Okay, we're working towards preparing for next Tuesday's test. So next Tuesday's test will be also 8 multiple choice questions, but these will be second semester topics. So we'll work through pages 9 through 12, and then 19 through 22. Those will be your review pages. Okay, so let's go to page 9. Okay, so the second semester topics, here they are. We have Riemann sums, like left rectangle, right rectangle, middle rectangle, trapezoids, approximation, first theorem, second theorem, average value theorem, integration rules, like and also use substitution, solving differential equations, and then area volume. We probably need to do a bit more review since this is the very final topic that we covered, but we haven't done any review since we covered it in March. So we'll go back and do review disk, washer, method, and cross section. All right. So today, see if we can get through as much as we can from page 9 through 12. Okay, so the graph of f is shown between 0 and 4. Let L, R, and T be left Riemann sum, right Riemann sum, and trapezoid approximation. Which of the following statements is true? So between those approximations, we want to be able to tell which one is going to give the lowest area approximation, which one will give the highest, and then where does the actual area land? So the integral from 0 to 4 is the actual area. So let me just kind of shade in what we're trying to approximate. Okay. So let's think about left Riemann sum and right Riemann sum. So left Riemann sum is where we're going to take every point where the real number is where the whole number is going to hit the graph, and we're going to draw rectangles stemming from the left endpoint. So what do you think this is going to do? These rectangles, will it under approximate, right? So it's probably going to be the least. So looks like A and B are going to be a good option for us to consider as our least value. Okay, what about a right Riemann sum? Okay, so every time we attach to the graph, now we're going to let the right endpoint represent the height of the rectangle. What do you think this is going to do? Over approximate, right? So so we probably are going to be staring at that as the largest value, right? Okay, so we kind of already know what our answer is going to be, but there's one more thing I want to discuss is trapezoids. So trapezoids is where we take every point, and then we're going to just go from tip to tip. So now we see that trapezoid is going to do a pretty good job of approximating, right? But what about the trapezoid compared to the actual area? Will it be slightly over or slightly under? Slightly over, right? And the reason why is because this graph is what? What shape is this? Concave up, right? What if the graph was concave down? Then your trapezoid is going to do what? Going to slightly under approximate. Yeah, so the shape of the graph is going to indicate whether your trapezoid is going to be more than the area or less than the area. So answer choice A is our best bet. Okay, number 2. For time greater than 0, the height is suspended from a spring given by h of t. What is the average height? So we want to find the average value. So average value theorem, let's review what that is. Is 1 over b minus a, integral from a to b of f of x. This is what the rule tells us. Okay, so we're always going to be provided what a and b and f of x is. We just have to kind of go through our integral process. That 1 over b minus a is just going to end up being a coefficient. It's going to be some number that's going to hang out in front. Maybe I'll need more room than this, so I'm going to make sure I can work this through with you providing enough room here. So what do you think? What's my a and b value? 0, 2, right? And my function is just going to be this h of t, right? So I'm just going to put everything in place. And this is meant to be a non-calculator question here. Any questions here with the setup? So really, it's just going to be a coefficient of 1/2. We can either wait to distribute until the end or distribute now. That's fine if we want to distribute now to get that out of the way. So I'm just going to go ahead and just split this up because I know this 16 is going to be easy. That's power rule. But this 7 cosine pi t over 4, I got to go through what? Yeah, use substitution. So I'm going to just do a little bit of cleanup. So if I'm going to distribute the 1/2 through, so I'll make this 16 over 2, which is going to be 8. And I'm going to just separate the rest of it here. 7 over 2. Okay. It does seem a little messy having to do all this at once. So what if I just treat it like 2 separate problems? We'll do the integral here, we'll do the integral here, and then we can evaluate the bounds separately as well. Okay, easy one is just going to be 8. The integral of 8 is just going to be what? 8x. In this case, the variable is t. Yeah, so 8t. And then we can do half bracket between 0 and 2. And that's just going to be upper bound first. 8 times 2 is 16. Minus 8 times 0, so 16. Okay, so we know that this integral will just give us 16. Okay, we just have to figure out what this side is, and we can add the remaining parts at the end. Okay, now this part, we got to go through a little bit more steps, right? What's our u value? Yeah, so that whole thing inside the parentheses. Okay, we want to go through u substitution, so we know what coefficients we got to deal with. So what's the derivative of pi over 4t? That's what? Just pi over 4, yeah. Just the coefficient. We know that degree 1 is just going to drop to a constant. Okay, I'm going to cross multiply and solve for dt. Okay, replace this with u, replace dt with 4 over pi du. Push all this mess out in front. 28 over 2, that's same thing as 14 over pi. Cosine, what's that? What's the antiderivative of cosine? Just sine. Replace sine back, replace the u back with pi t over 4. And then upper and lower bound from 0 to 2. Two pi over 4, which is the same thing as pi over 2. minus 14 over pi sine of 0. Sine of 0 is just going to be 0. Okay, so sine of pi over 2, that's nice. That's just equal to 1. So 14 over pi is the only thing that's left. Yes, question? So the integral of cosine is just going to be sine of u plus c. We don't do times u prime. That is for derivative. And also the du kind of takes care of that backwards chain rule that we're working from. So the whole right, this whole u substitution and the bounds gave us 14 over pi. We have 16 from our constant, and we add those together, and that's our answer. That's our average value. Okay, any questions here? Okay, let's look at number 3. The limit as h approaches 0 of 1 over h. This seems like a mess, right? But we know it's a limit problem, so why don't we just get our numerator and denominator to show up? Because anytime I see a limit problem, I'm always thinking maybe it's going to be something I can just use L'Hopital's rule for. Right, I got my numerator and denominator over each other. All right, what's the first thing that we can do with a limit problem? Again, right, so if I plug 0 in for h, what do I get? 1 to 1. What's going to happen if I have 1 to 1? 0, okay? And the bottom is also 0. So that gives us the green light to apply L'Hopital's rule. The L'Hopital's rule says take the derivative of the numerator and take the derivative of the denominator. So here's the derivative of my numerator. I'm going to just spell out what I want to do. Okay, let me do the denominator first. That's easy, right? What's the derivative of h? Just 1. Okay, so I know that's going to be just 1. Now, the derivative of the numerator seems a little bit more complicated, but what does this remind you of here? What can we do? Cancel out, right? This is basically second theorem. So second theorem says I can wipe out these two operations. I just have to do something with this upper bound. I'll take this upper bound and do what with it? Plug it in for x, and then multiply by the upper bound's derivative. Yeah, in this case, what's the upper bound's derivative? Just 1. Okay, so it looks like nothing's going to come out of it. It's just we just need to plug it in. So square root of 3 plus 1 plus h quantity squared all over 1. Okay, so now that we have our derivative all spelled out, what's our final step? Yeah, we're gonna plug that 0 back in, right? Our whole goal is to try to find a limit, trying to get a real number instead of 0 over 0. So if I plug 0 in for h, I get 1 squared. 1 squared is 1. 1 plus 3 is 4. Square root of 4 is 2. Okay, so an application of second theorem as well as L'Hopital's rule. Okay, number 4. If uppercase f of x equals this, find the derivative. So again, this is kind of asking us to apply second theorem, right? I want to write out what I'm about to do here. I want to find the derivative. Or d over dt. d over dx. Integral from tangent of x to 0. Okay, so again, I would like to, I know I'm going to have to apply second theorem. I know I'm going to have these two wiping out each other. What do you notice about the bounds, though? What could we do? Yeah, let's flip it so that we can get that upper bound to be the variable and the lower bound to be the constant. If I flip it, I got to do what? Negative. Yeah. Sorry, I wrote dt twice here. Okay, so now let's go through second theorem. Second theorem, we know these can wipe out. Plug the upper bound into the variable. Times what? Yeah, tangent's derivative is secant squared. Sorry, this one is a little bit more difficult because we don't see the answer choice in front of us. There's actually a trig identity of 1 plus tangent squared, which is secant squared. So this is actually negative secant squared x over, and then this also becomes secant squared x, which is negative 1. Okay, I'm not gonna put that on the test for you where you gotta do another set of identities to get to your answer, but this is that's what's more important. Okay, but that's why the answer choice is doesn't show that. It's actually cleaning that up a little bit more here. Unlikely. Yeah, it's pretty rare that they stick an identity in there. I think, but I do think one identity that we all should know is cosine squared plus sine squared equals 1. I think that is something that you could see. Again, it's not likely that they're going to stick these identities in your AP exam. Okay. Okay, page 9. Okay, page 10. Okay, the graph of a differentiable function is shown. We have h is the area from 0 to x. Which of the following statements is true? It's asking about what h is. You know, h is going to be the area under the graph. And then let's build h prime and h double prime so we can have something a little bit more easier to interpret. So let's just go ahead and get all of the derivatives out of the way. We know h is just the area under the f graph. And h prime is just the derivative of this. Oh, sorry, thanks. We know that h is the area under the f graph. We know h prime is just the derivative of this expression. And what's going to happen here? This is going to turn into what? Yeah, we know derivative integral cancel each other out. Those become f of x. So therefore, h double prime will just be what? F prime, yeah. So they're asking us to compare between h of 6, h prime of 6, and h double prime of 6. So let me just put everything in place there. We know h of 6 is the definite integral from 0 to 6 of f of t dt. So it's going to be this here. What do you know about this value? Negative, right? So I know maybe it's like negative. I'm just going to create a rectangle out of this, maybe like negative 15-ish. Something like that. I'm just doing a really ballpark value here. Okay, what about h prime of 6? H prime of 6 is f of 6. What's f of 6? Okay, 0. Okay. And then h double prime of 6 is just f prime of 6. What do you know about f prime of 6? Positive, right? Maybe 1 I'm just guesstimating what that slope is. So then between 0, 1, and negative 14, we can decide which one is the smallest, right? We know the displacement is going to be the smallest because it's negative, followed by the 0, and largest is going to be the positive slope, which is 1. And a lot of second theorem here. Okay, number 6. Let the function be defined by f of x is the integral of which of the following is the graph concave down. So if this is the f of x, and if I want to do anything with concavity, I got to make my way down to the what? Second derivative. So let's build them. Let's build our way down. Okay, so derivative is just, I got to wipe out that integral notation, right? What's going to happen if I take the derivative of the integral? Yeah, just plugging the x, right? This expression is not going to change. I can just wipe this out and just replace every x with, sorry, every t with x. So this is my f prime. So now f double prime, it's just another derivative down, right? So now we can go through power rule. 2x cubed becomes 6x squared. 15x squared becomes 30x. 36x becomes 36. Okay. So if I want to find critical points, I can set this equal to 0. I can do GCF, factor out a 6. Continue factoring. Multiplies to be 6, adds it to be negative 5. Negative 3 and negative 2. Solve for x. I get 2 and 3. Okay, so now my second derivative sine line. Choose values in each subinterval to test. I'm going to test 0, I'll test 2.5, and I'll test 4. Okay. Into my second derivative function, I plug 0, 0 minus 3, 0 minus 2. That's 2 negatives. That gives me positive, so concave up. 2.5, that's negative and positive, which is negative. Plug in 4, positive and positive, which is positive. So concave down, I can say from which, on what interval? 2 to 3, yeah. Okay, find the derivative. So there's all these second theorem, right? We're getting a lot of practice with second theorem. So what would this turn into here? Yeah, natural log of 2x quantity cubed plus 1 times upper bound's derivative, yeah. So let me clean this up a little bit. 2 natural log of 8x cubed plus. Okay, number 8. F is given as 2 sine of e to the t over 2. G is the antiderivative of f. So let me just write out what that means. We know G is the antiderivative of f. Okay. So we know that g of -1 equals -2, then g of 3 equals. So we know that this is basically, f is basically the derivative of g. Because if I find the derivative, I can see that, okay, that's just basically that relationship. Anytime I'm looking for a location and I have a starting point, I like to think in terms of final location equals initial location plus displacement. And typically, I think in terms of particle motions. So this is the formula that I have in my head. X of A equals X of B equals X of A plus A to B of X prime. Final equals initial plus displacement. So in this case, what's my final? What am I looking for? G of 3. So G of 3 is equal to G of -1 plus however much progress I can make between my two endpoints. And then my G prime is this, right? That's my F. 2 sine of. And this is meant to be a calculator question here. Anytime you see decimals as your answer, that's got to be a calculator question. So we plug this in our calculator. Make sure you do everything in terms of X. G of -1 is -2. So -2 plus whatever this decimal is. And that gets us 2.255. Okay, let's do another particle motion problem, number 10. Actually, number 10 and 11, they all kind of have a similar feel to it. It's all kind of that final equals initial plus displacement. So let's see if we can get through number 10 at least. Okay, a particle moves along the y-axis. Velocity is given by v of t. The position is 4 at time t equals 0. What's the position when the velocity first equals 0? So that's our first goal here. Trying to figure out when is velocity equal to 0? So after we find that time, then we can move forward. So we can set 0 equal to the 2 sine of t squared minus 2 minus 1. You can graph this and then look for the what? X-intercept, yeah. So I'm going to just fast forward it. Ends up being 1.379. So it's basically saying, what is the position of the particle at this moment in time? So I'm going to say, I'm going to find my location at this moment in time. Initial position is x of 0. And then my displacement is from 0 to 1.379 of my velocity function. I can plug this in the calculator, get some displacement, add it onto my starting point, and that's going to tell me where I'm going to end up. This calculator work would give us -1.533. You do math 9 of your velocity function. So we're starting at 4. We're moving left 1.533 at 1.379 seconds, or that time. We're going to end up at location 2.466. Okay, I'm going to check the rest of this packet probably on Monday. So every day we're just going to, I think we could just spend our class period just finishing up this packet together in preparation for next Tuesday's test. Okay, so I'm not going to check any homework until the rest of the packet is due, which I'll make it next Monday or next Wednesday, something like that. But I think we could get it done before our test. Okay, all right, come get your phones. Sure.